Hi everyone, this is Dr. G. Srinivasa Gupta, Professor of Mechanical Engineering Department from VJEC Institute of Engineering Technology. Today we are going to discuss as a part of the Dynamics of Machinery course a concept on balancing of inline engines. So the advantage of inline engines maybe contains 2 cylinders, 3 cylinders, 4 cylinders. But the advantage is we can balance some of the primary forces and secondary forces and couples. We will see what we can do the balancing of inline engines. What is inline engine? First we need to understand. It is nothing but the cylinders are arranged in a straight line along a common crankshaft. All the cylinders are arranged in a straight line in a common crankshaft. So that cylinders arranged such that in the straight line. Okay, this is cylinder 1, cylinder 2, cylinder 3, cylinder 4 like that along the crankshaft. This is crankshaft. So these cylinders are aligned. I am drawing only center lines of the cylinder 1, 2, 3, 4. Okay, like this number of cylinders. This is called inline engines. Okay, it mainly deals with the reducing unbalanced forces and movement due to reciprocating masses. Okay, but that is our object. So this inline engines, we know that engines in which all cylinders are arranged in single straight line along crankshaft length. Okay, so an inline engine is engine when cylinders are placed one after the another in a straight row. All pistons move parallel to each other and they share a common crankshaft because cylinders are arranged in a single crankshaft along the length. Okay, you can see diagrammatically cylinder 1, cylinder 2, cylinder 3, cylinder 4 arranged on single crankshaft. This is the diagram. Okay, so now we are going to, we know that what is the unbalanced force. If a reciprocating mass is transferred to the crank pin, then what is the unbalanced force? That is inertia force due to piston and whatever reciprocating parts. Then the axial component parallel to the cylinder axis of the resulting centrifugal force represent the resulting centrifugal force of mass attached to the crank pin. So that axial part, axial component, which is represent the primary unbalanced force. Okay, if crank is kept at an angle of 2 theta, then you will get secondary unbalanced force, like that couple saws. Consider a shaft consisting of 3 equal cranks, okay, unsymmetrically placed. Okay, we have a shaft and consists of 3 equal cranks. That is, suppose let us say one crank. So this is the crank arranged. Okay, this is one crank. Second crank placed at a distance, that is, let us take second crank is this one, okay, on the shaft, and third crank along this shaft only. Okay, third crank in this direction. Let us sorry, in this direction. Okay, this is third crank, second crank, first crank. Okay, it is obviously connected with the connecting rod. Okay, and if you want to see orientation, this is like this, and piston cylinder like this. This is all. This is connected with the connecting rod, and you can see along the what is the inclination. Then piston guiding in the cylinder. This is cylinder center line. It represents. Okay. Similarly, in this case, this is the connecting rod. Okay, connecting rod, and this is the center line, let us say, and piston, it is connected, right? These are 3 cylinders in a row. This is, let us say, M1, M2, M3 are masses of reciprocating parts. That is piston. We can just consider. So these 3 cylinders equal cranks unsymmetrically placed. See this. This is the direction, orientation of this crank if you want. This is the orientation of this crank. This is the orientation of this crank. This is the orientation, as you know that. So this is unsymmetrically placed. Okay, the crank pins carry equal equivalent of 3 unequal reciprocating masses. Let us say crank pins carry equivalent masses. Equivalent masses in these reciprocating, these are reciprocating masses. So what happened? These reciprocating masses leads to the primary force, unbalanced force, that is along the line of action. We can say sum of all these forces. Suppose M1, M2, M3, we said M1, M2, M3. We can write sum of all these forces sigma mr omega square cos theta. Okay, M1 R1 omega square cos theta, M2 R2 omega square cos theta. This is summation. Similarly, primary couple, you know that. How do we calculate? Distance between the cylinders. Okay, if you take reference plane 1, then you can evaluate couple from other masses on this reference plane. That we can get using this relation sigma, sum of the algebraic sum of all couples. That is M1 R1 L1 omega square plus cos theta M2. This is components along line of stroke, primary couples. Similarly, secondary forces, secondary couple, we can write the relation MR 2 omega, actually this is 2 omega whole square by 4n cos 2 theta. This is a secondary force, that is MR omega square by n cos 2 theta. You can write here. This is something not there. Okay, are you able to understand? And MR omega square L cos theta couple. Force is concerned, no L is there. MR omega square by omega square cos 2 theta by n. Similarly, secondary couple, you can write MR 2 omega whole square by 4n or omega square by n. Okay, so into L. L cos 2 theta. Here also L must be there. Okay, understand or not? So you can take any plane, reference plane, you can write couple equation or force equations. You know directly you can write algebraic sum of all the forces on all the cranks along the line of stroke. Actually, along the line of stroke is the unbalanced force due to reciprocating masses. That component we are going to talk about here in these 4 relations: primary force, primary couple, secondary force, secondary couple. So these relations we discussed much about on these relations, how to write in previous lectures also. You are able to understand this much, I think. In order to solve the above equations graphically, then we need to draw force polygon and couple polygon. So we can find any, suppose these are the cylinders. How do we draw force polygon? Suppose first force is M1 R1. This is acting in this direction. M2 R2. This is acting in this direction. Okay. M3 R3. This is acting in this direction. Suppose this is M1 R1, M2 R2, M3 R3. Because omega square is common for all, we can take scaling factor, that one. Then the closing side is going to represent the resultant of all these. Okay, so this is closing side, this is representing resultant of all these. So this must be balanced, means it must be acting in this direction. Otherwise, resultant of this M1 R1, M2 R2, M3 R3 is this one. So balance, should be balanced, means you know that this one, if it is balanced, sigma mr omega square cos theta, so algebraic sum must be 0. So you see that resultant is this one. Okay, resultant inclination of resultant with the line of stroke. This is the line of stroke, or horizontal you can say. This is theta. So you can understand how we are going to get draw this polygon. Okay, so in order to solve the above equation graphically, first draw force polygon, then axial component of resultant force, whatever resultant force you have, here you have drawn, then axial component is, this is MR, we can say this component, this is axial component, MR resultant, RR, we can say MR, okay, cos theta is the resultant. We can write, is it or not? Okay, this is the resultant along the line of stroke. That is unbalanced force, we can say. This is the resultant unbalanced force. This we are going to write here for cos theta. Okay, multiply by omega square provides the primary unbalanced force on the system at that moment due to all the cylinders placed in their corresponding location. This unbalanced force is 0 when it becomes theta. You know that we have seen this theta becomes 0, then it is maximum. When theta becomes 90, this is becoming 0. Okay, theta is 90, it is 0, and maximum when theta is 0. Similarly, other components also you can see. In case of force polygon enclosures, suppose this polygon we have drawn. This polygon already, because of all these cylinders, it is enclosed like this. It has come, let us say M3R3. Suppose, then it is closed. Then there is no unbalanced force. Okay. In case of force polygon enclosures, the resultant as well as the axial component will always be 0, and the system will be in primary balance. What is that meaning here? This is enclosures means the horizontal component of it and vertical component of it must be 0. Resultant is 0. That is okay. Horizontal as well as vertical component of this force resultant is 0. Okay. So you are able to understand this much up to here. How to write primary force, primary couple when cylinders are located along the shaft, along the length of the shaft. Then the equivalent amount in horizontal along the line of stroke or cylinder center line direction, that force which gives the unbalanced force, primary force, similarly couple, secondary force, secondary couple. Okay, when these are going to 0, when these are going to maximum, in other crank angle position, this may have some value. Okay, we are going to see all such details. Okay, to find the secondary unbalanced force, similar way we can draw these polygons and we can find. First find the position of the imaginary secondary cranks, then transfer the reciprocating masses and multiply the same with 2 omega square by 4n. That is omega square by n to get the secondary force. In the same way, primary and secondary couple MRL polygons can be drawn for primary and secondary couples. You are able to understand, I think, this secondary unbalanced force. We are going to take the angle corresponding to, that is 2 theta crank angle. Okay, so here we need to write secondary. Already we have written secondary force cos 2 theta MR 2 omega whole square by 4n cos 2 theta. Here 2 omega whole square. Okay, here written correct. Okay, so similar way we can draw polygons and we can get the resultant. If it is a closed polygon, then resultant is 0. Okay, that is balanced condition, right? Then 2-cylinder engine, let us take for example. Okay, consider inline 2-cylinder engine, cranks which are 180 degrees. So cranks are 180 degrees, then how do you make that diagram? Okay, 180 degrees cranks. So 2-cylinder engine, this I am taking, okay, shaft, okay, shaft. Then 2-cylinder engine, this cranks, this is one crank, let me check, draw, and second one is this one, okay, this is the crank, second one is this, second one is this one, okay, second one, okay, this direction, because 180 degrees there. Okay, I will draw here. Okay, one crank, this one crank, then second one is this position. Let us take, this is the position. Okay, so these are 2 cranks here. Okay, this okay, here along this this is the piston connected with the connecting rod. You need not, here also this is the piston connected with the connecting rod, you can say here. Crank orientation for each 1, 2 cylinder. This crank orientation is, we can say this is theta. Second one is how much? This one is with this is okay. How much angle? 180 plus theta, because this is in this direction, this is here, this is 180 plus theta. Okay, 180 plus theta, this is theta. Okay, these 2 cranks you can see crank position along the with respect to center line. Similarly, crank position with respect to center line, this is theta, this is 2 theta, 180 plus theta, right? This is 180 plus theta, right? Okay, this is primary cranks, okay, position. So then primary cranks you will giving forces, corresponding forces. So primary force, what is primary force? You will get from crank 1 mr omega square cos theta. You know that primary force is mr omega square cos theta. Secondary one is mr omega square cos 1 theta plus 180 plus theta, cos 180 plus theta. Are you able to understand? So this is because this angle is crank orientation is 180 plus theta. Okay, from here. Okay, this is the crank orientation from here. Right, this is the crank position, then crank orientation is theta. So primary force is this one. This you can see cos 180 plus theta minus cos theta. So you are going to get 0. Means in this position, if the cranks are positioned at 180 degrees each other, then the primary force becoming 0. Let us see primary couple. Primary couple means along the center line, the distances, let us say from this distance L by 2 and L by 2. L by 2 and this is L by 2. Central line of the cylinder from the crank position where mass is attached. Then you can write primary couple is mr omega square. It's straightforward, cos theta into L by 2, cos theta into L by 2 plus, okay, this is in this direction, this one opposite direction. So that's why you are going to write minus L by 2 minus side, mr omega square cos 180 plus theta, cos 180 plus theta. Okay, this becomes resultant. This is going to equal, okay, if you see that cos 180 plus theta minus cos theta, then this is becoming mr omega square cos theta into L. This is the magnitude. Okay, so this magnitude, this value becomes maximum when theta equal to 0 and 180 degrees. So the unbalanced force becomes maximum at theta is 0 or 180, and theta 90 and 270, this becomes 0. Okay, are you able to understand this one? If two cylinders arranged on a shaft, inline cylinders, then you can have primary force 0, primary couple, you will have unbalanced couple mr omega square L cos theta. So maximum value also you can see at theta 0 and 180 degrees. Now what about secondary force? Secondary force, how you can write? Okay, as usual, mr omega square by n cos 2 theta plus cos this is talking about inline two cylinders, primary, this is the diagram. Secondary diagram also you can make. Secondary diagram I am going to make again. This, see here, this is one crank. Let us say, what is the orientation secondary diagram you need to take? You need to take orientation of secondary diagram as theta plus 2 theta plus theta is 180, then 2 theta is 2 theta plus, because theta difference is 180 each difference between crank positions of the cylinder 1 cylinder 2. So 2 theta, theta is theta plus 180, 2 into theta plus 180. So you will get 2 theta plus 360. So crank positions are like this in secondary portion. This is 2 theta. This one you can see. Okay, this is in which position? This is in this one is this is 2 theta for here, 360 plus 2 theta. Again same position it will get 360 plus 2 theta. This is, you can say this is also 2 theta, because theta is differ an angle of 180. Okay, 2 theta is 2 into theta plus 180, 360. Okay, this is the position. In this position you can have primary force and secondary force and secondary couple. We can write those. Secondary force is mr omega square by n cos 2 theta, and second cylinder mr omega square by n cos 360 plus 2 theta. Resultant you are going to get 2 mr omega square by n cos 2 theta. Okay, secondary force. Previously in the primary force you got 0, but secondary force is remain with some magnitude. Here also maximum you are going to get when theta equal to 0 or 180. Okay, 180, 360 or 540, so and so we can write. 2 theta. 2 theta is 0 or 180 or 360 or 540. You are going to get the secondary force maximum magnitude. Okay, then theta becomes 0, 90, 180, 270 correspond to this. Secondary couple you can write mr omega square n into L by 2 cos 2 theta plus Again similar way, minus L by 2 into cos 360 plus 2 theta. This value becoming 0. So there is no secondary couple in case of two cylinder inline engine. There is primary force is 0. Primary couple has some magnitude, depends on crank angle or crank orientation. Similarly, secondary force has some magnitude, depends on crank orientation, it may become 0 also, and but it is not always 0, and secondary couple is becoming 0. Primary force and secondary couple are going to be balanced for certain angle of theta, any angle of theta. Okay. So for certain angles, the other components, say, primary couple and secondary force may become 0, but it is not always 0. But primary force and secondary couple always at any angle of theta, it becomes 0 for this case of arrangement of cylinders which are cranks located at 180 degrees angle each other. So this is I think you are able to understand. You can write diagrammatically also, you can use and you can construct. Suppose for example, this secondary force becoming how much? This is secondary force is having some magnitude. How we are going to get? So this is the crank, one crank position, secondary I am drawing. This is 2 theta, and second one is what? This is also 360 plus 2 theta. So these two horizontal component. Okay, if you magnitude wise, if you mark and draw the diagram, and this horizontal component is going to give your value, which is 2 mr omega square by n cos 2 theta. You are going to understand like that. This is force, and like that couple also, couple becoming 0. How it is going to become 0? For 2 theta crank rotation, this is the couple, and because it is 360 plus that is opposite direction, other one is for second cylinder, this is the couple. This summation is becoming 0. You are going to understand. This is mr omega square by n into L by 2. This is also mr omega square into L by 2 by n into L by 2. So these are opposite direction. These are nullified, neutralized. This becomes 0. Like that, primary force and primary couple also you can make these diagrams. Are you able to? I think you are able to understand inline engines, primary forces, primary couples, secondary forces, secondary couples, how we can write these expressions, and magnitudes also we can verify. Okay, secondary couple and primary force can be balanced at an angle of theta for this case of arrangement, and primary couple and secondary force are depends on angle of crank orientation at any instant. Okay, this is about this. Now, so what you need to remember that to find primary force and couples antically we want to make that. Then the positions of the cranks have to be taken in terms of theta. You know how forces can be calculated. Mr, algebraic sum of mr cos theta, and secondary forces mr, okay, mr cos 2 theta. You can see. Okay, we can write these must be, if these become 0, then it is balanced. Similarly, couple you can write mr L cos theta, algebraic sum of all. Okay, with respect to any reference plane, this couple components must be 0. Similarly, secondary mr L cos 2 theta must be 0 for balancing. If there are any resultant, then there is not right side quantities, some value you are going to get. As it is a rotating system, the maximum values or magnitude of the forces and couples vary instant to instant and are equal to values as given by the equivalent rotating masses at the crank pin. That we have seen just now. If a particular position of the crankshaft is considered, suppose particular position you want to know, then the above expressions may not give the maximum value. For example, the maximum value of primary couple in this case is found to be mr omega square L. Primary couple you have seen. This is the value which is obtained when the crank positions are 0 degrees and 180. Okay, for all values it is not same. Okay, however, if the crank positions are assumed at 90 degrees and 270, then because cos of that angle, it becomes 0. So this magnitude is varying depends on position of the crank, instant to instant. You are able to understand this is also, I think. Suppose for example, in case of any particular position of the crank, let us consider, then in that case what we need to do is both x and y components of the force are coupled can be taken to find the maximum values. For example, if the position of the cranks are considered 120 degrees, position of the cranks are 120 degrees each other. Suppose this is the crank position, this is 120 means crank position. I will draw like this. Okay, this is the crank position initially 120. Okay, for example, position of the cranks are considered at 120 degrees and 300 degrees. This is 120, this is the one position, and second one 300 degrees. 300 means you can say this is 180 and 270 and 300. Okay, somehow like this. So 300. Okay, this is 300. Once 120, 300. This is the position we kept the cranks. Then x component of this balancing masses we can write analytically mr omega square L by 2 cos couples L by 2 cos 120 plus minus L by 2 cos 180 plus 120. We have seen 300. So you are going to get minus 1 by 2 mr omega square L. L is distance between the center line of the cylinders. So that is, this is the L. Okay, you are able to understand, I think. Then y component you can write mr omega square L by 2 sin 120 plus minus L by 2 sin 180 plus 120, that is 300 orient. You are going to get root 3 by 2 mr omega square L. Then primary couple you want. So primary couple you want total, then square root of x component square plus y component square is giving mr omega square L. Okay, this is about this any position of the crank you want to write find primary couple or secondary force, you can write similar equations. Let us consider one numerical exercise. Okay, and then we can see how we can able to solve that. Here in this numerical problem, let me read. A 4-cylinder oil engine is in complete primary balance. 4 cylinders. This is the 4 cylinders. Complete balance it is said. So remember, all these couples are primary and secondary. You need to get 0. Okay. Primary balance it is said. Primary balance means primary force, primary couple must be 0. It is not talking about secondary. We will see. The arrangement of the reciprocating masses in different planes is shown in figure. This arrangement is given. Cylinder 1, okay, cylinder 2, cylinder 3, cylinder 4. Masses are given. This is 480 kg cylinder 4. Okay, this is reciprocating mass. How much we have? This is 590. This is not given. M2 second cylinder 1, 2, 3, 4. Okay, these masses, reciprocating masses, some of the values are one value. The second cylinder, this mass, reciprocating mass is not given. Other are given. The position of the cylinders, okay, arrangement, the distances in these planes of the cylinders are given. This is 2.8 meters. Okay, and cylinder 1 and cylinder 2 distance is 1.3 meters. And cylinder 4 and cylinder 3, this distance is also 1.3 meters. This much is given. Then what you need to do is the stroke of each piston is 2 mm given. Stroke means you know that the movement of the crank from piston from top dead center to okay, in outer dead center to inner dead center. That is, the crank is going to rotate its 2 times the radius if the piston moves from top to outer dead center to inner dead center. Then if you want to crank length, because crank will take the motion from its extreme positions and completes its 180 degrees, and at line of stroke, along the line of stroke, it is 2 or mm the stroke. So then crank length, you know that 2r by 2, that is it is becoming radius of the crank. You can see this one. Okay, if we want diagrammatically, the crank position extreme, this is inner dead center. If crank is going to some position and it is going to reach, then piston is okay some position here. If crank is reached, again it is moving and reaching here, then it is piston is going to get its position. This is outer dead center, this is inner dead center position of the piston. Similarly crank outer dead center. So crank is this is stroke length. Stroke length means this one equal to this, then this is given as 2r, then crank length is r, 2r by 2, that is written here. Okay, now here in this diagram take 2 as the reference plane and theta 3 take it as initial position of reference is theta 3 is 0. Then we can write the couple terms m1 r1 l1, okay, 380 into r into my because couple with respect to reference plane is here, reference plane is 2, then one is having the couple or the moment with respect to reference plane clockwise, and 3 and 4 having anti-clockwise direction moments. So that's why we have written m1 r1 l1 is 380 r into minus 1.3. Okay, similarly m3 r3 l3 and m4 r4 l4 corresponding values we have substituted and we have used positive because these are anti-clockwise movement about reference plane 2 given. After solving these equations we are getting this is if we can write as I mentioned that this relations sigma MRL cos theta primary forces are constant. If you use this and you write all these, then you will get because balanced it is given complete balance primary forces and primary balance. That means forces and couples both. Then if you take force components, sigma MRL cos theta must be 0. Similarly MRL sin theta must be 0. If you write that and couples also you can write corresponding equation. So if you use these equations and squaring both sides and addition, you are going to get from the equations theta 4 you are going to get, that is okay how much, because you know that our theta 3 is 0. If you solve these equations, okay, MR L cos theta couple equations, so MRL sin theta algebraic sum, then you are going to get theta 4 equal to 167.9 or 192.1. We will choose any one and we will proceed further. So we choose theta 4 is 167.9. I think you are able to write say sigma algebraic sum of all couple components of along the line of stroke, and similarly perpendicular line of stroke couple components MRL sin theta algebraic sum you can write and you can solve these. You are accustomed to do so many problems previously also. So solving these equations will give theta 4 values 2. We will let us take theta 4 is 167.9. Use this in first equation, obviously we will get theta 1. Okay, so theta 1 theta 4 we are going to get in this way. Okay, writing and solving again force equation. If you solve force equation, you can write and solve force equation using this theta 3 anyhow reference we have taken 0, theta 1 theta 4 we have values got from couple equation. Then force equation if you write, you are going to get m2 and theta 2. Okay, because sin cos terms we have, if you divide one over the other you are going to get theta. If you use that theta any one equation, you are going to get m2. Okay, this is a regular procedure. We are having seen so many numerical problems when we attempted. This is all about unknown quantities we can find. These inline engines are very simple to attempt, and basic equations are algebraic sum of force components, algebraic sum of couple components must be 0. You want to construct couple polygon, force polygon, and you can find unknown orientations. You can always in any such numerical problem, generally we are going to construct couple polygon, then we can find orientation. Like here theta 1 theta 4 we have from couple equation only we are going to get. Then you can construct using that orientation value force polygon, then you are going to get unknown force components. So this is the procedure in general for any such type of problem in inline engines. You can also have here 4 cylinder given. Number of cylinders you can have inline engines 6 cylinders also. the problem solution is similar procedure. You can apply and you can solve unknown quantities asked in the problem statement. This is all about inline engines. We are going to see next in our next lecture radial engines. How do we get balance radial engines and finding unknown quantities any required, and what is the specialty of radial engine we are going to see in our next coming lecture. Thank you one and all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.